All right, day 2, standard normal distributions. So the mean, median, and mode are all going to be equal if it's a standard normal distribution. The normal curve is bell-shaped and symmetric about the mean. In other words, if you drew a line down the center and folded it in half, it would match up. The total area under the curve is equal to 1. So think about those percentages we all did on the previous lesson. All those percentages add up to 100%. The normal curve approaches but never touches the x-axis as it extends farther and farther away from the mean. Okay, so you can't ever draw it that accurate, it's human error, but theoretically it will never touch the x-axis. All right, so getting to the standard curve. All right, and remember, if you have to pause anytime, just do so. Okay, this is just ridiculous. Here we go. So, if you look here, the mean is 0 and the standard deviation is 1. Okay? So a normal distribution can have any mean and any positive standard deviation. Okay? So remember, it's kind of like absolute value. If standard deviation is 1.5, it's 1.5 left and right of the mean. You're just adding and subtracting, but the standard deviation itself is positive. The mean gives the location of the center and the line of symmetry I referred to before. The standard deviation describes the spread, or how wide the distribution is. So if you look here, a little blurry, sorry. Okay, you have what are called inflection points. That's where the curve starts to change the slope. All right, so on the first one, on A, the standard deviation, the mean is 3.5. So that dotted line is the mean, and that's the middle of the curve. The standard deviation is 1.5. So if you go out 1.5, you hit 5 and 2. That's where the inflection points are. And that's where you would draw the line that we've been drawing previously, like so. On B and C, notice the standard deviation is both the same, 0.7. But notice this, the mean is different, 3.5 and 1.5. So this right here, almost got it, is the same as this one right here. It's just starting at 1.5 for a mean instead of 3.5. So if I just did this, you can see where that one would be, close to it, if I did that line down. Now, there's a link here to Desmos, and it takes you here. Now, don't worry about the fancy equations here. All we're doing here is playing with the fact that if you look at the mean right here, I can change the mean with this slider. And notice how it goes to the right. The mean is moving down to the right, or I can move it to the left. All right? I can bring it back to 0. And S is the standard deviation. So right now, it's a standard deviation of 1. So the inflection points are at 1 and -1. I can change the standard deviation like so and get a different shaped bell curve. And again, I can move this left and right. So you probably have all used decimals at one point or another. This is just to show you how you can use it and how it affects the curve. All right, moving on. So, which curve has the greater mean? Okay, well, if you look at where the mean is on A, It's up there around 15. And the mean on B is around 12. So who has the higher mean? A does. Greatest standard deviation. Remember, that's how wide it is between inflection points. So B has a greater standard deviation. It's wider. All right, so this part should be very familiar from Algebra 2. The standard normal distribution. Normal distribution with a mean of 0 and standard deviation of 1. We already said that. For any x value, you can be transformed into a z-score. And the z-score is what we're going to use to reference to find area under the curve. Now, your Algebra 2 teacher might have said actual. That's what I use in my class. Actual minus the mean divided by the standard deviation. So whatever score you have, minus the mean divided by the standard deviation. Okay? We'll talk more about that when we get into the charts. So, what are the properties of the standard deviation? The cumulative area, we've already said that, is always equal to 1. Everything under the curve equals 1. The cumulative area increases as you increase your z. The cumulative area for z equals 0 is 0.5. So in other words, that's half of the graph. If your z-score is 0, that's half the graph. And as your z-score increases, you're getting more and more of the area. And we'll talk about that. The cumulative area for z equals 1 is 0.8413. So in other words, let's look right above here. If I'm at 0, and my z-score is right here, this is 50%, 0.5. If I'm here at 1, this area is 0.8413, about 84% of the graph. And if I went out to 2, I would have a higher area under the graph. And if I went out to, because it's always shading to the left. All right? All right, so we're going to be using the chart, Table A, in the chart of the blue packet you received at the beginning of the semester. Now in here I've incorporated into the notes, it's not in your packet, but you have both packets there. I'm going to be bouncing back and forth between the table and the notes so you can see how to use it. Now we've done this already in Algebra 2. It should be hopefully coming back to you as you look at it. So let's look at z equals 1. Where did that 8413 come from? Well, if you look at the chart, okay, notice the first page of Table A is negative numbers. And if you look at the picture up here, the probability, these numbers are always everything left of the line. All right? It says here, lying below z. All right? So, if we look at this, all these numbers are negative, from negative 3.4 to 0. And if we look here, here's from 0 to 3.4 on the right side. Notice how these numbers are big. Okay, look all the way over to the bottom right corner, 0.9998. So this is from 0.5 to 0.9998. And the previous one is from almost 0, 0.003 to 0.4641. So the left side and the right side, oh, actually, if you look here, here's your 0.5. All right? Okay? So these are all the values left of center, and here is right of center. So when we look at 1.0, and look how this works. So here we have 1.0, 1.00, as opposed to 1.05. All right? That's how that works. So if we look at 1.0, there's the 0.8413. All right? Remember how I drew the line at 2 before and said, oh, it's going to be a bigger number? Well, let's see what 2 is. 0.9772. If we went up to 3.0, that'd be 0.9987. But what you can see from this chart is you have a lot of decimals, all the numbers in between. So when we looked here, we could look up, 1.72. All right? We want to know what 1.72 was. We would just go to our chart, find 1.7012. There it is, 0.9573. In other words, almost 96% of the data is left of that line. Okay, we'll come back to that. We'll play with that in class. Moving on. So, finding the areas under the curve. Areas to the left, okay? It always is going to show you the area left of that z-score. This is just a summary. Area to the right, if you ever want to know right of the line, we're going to do 1 minus that number. Okay, just simple mathematical calculation. So if we want left, we use the chart. If we want right, we look it up on the chart and then subtract it from 1. And if we're ever looking for an area in between two z-scores, we just subtract the big minus the small area. That's simple. All right, let's actually do some now. Find the area under the curve left of negative 0.99. Okay, so you're going to look in your chart. I'm going to go to the negative side. Negative 0.9 is right here, and all the way down. So I'm going to go all the way over 0.99, 0.1611. Or now, at first you might think that doesn't sound right, 0.99, but it's negative 0.99, okay? So, if you think about it that way, negative 0.99 is very far to the left, and therefore it's going to be a small percentage, okay? Next one. Find the area to the right of that number, okay? Well, we don't have to go back to the chart. We already know it's this. So we're just going to do 1 minus 0.1611. And that's going to be 0.8389, or 83.89%. If you think about it, it makes sense. Think about a dollar in money, okay? If you bought something that cost 16 cents, and you gave them $1, you get 84 cents back in change. And that's all we're doing here, okay? Left is what we're paying, right is our change, okay? Very simple. I always told my students in Algebra 2, anytime you see the word right, immediately, before you do anything, just write that. Just write 1 minus to remind yourself of that next step. That way when you fill in the number here, you remember to do that. Because a lot of times you get lost in looking up a chart and come back and forget to do the subtraction. So that's a good habit to get into. Find the area under the curve between negative 1.5 and 1.25. All right? So negative 1.5. Where's that? Well, here's negative 1. Okay, the board just is going to be that way. And since it's negative 1.50, it's just that. 0.668. 0.0668. Then we're looking up 1.25. That's on the positive side. So first we come to 1.2, and then we're going to go over 0, 1, 2, 3, 4, 5. There it is, 8944. And all we're going to do is subtract those. 0.0668. Okay? So 0.8944 minus 0.0668. And that is 0.8276. about 82.76% of the data is in between those two z-scores. Okay, last bit, and we did this again also in Algebra 2. It says, in baseball, player's batting average is the proportion of times he gets a hit out of the total times the bat. We have a player, let X be the batting average. The probability of X is approximately normal, with a mean of 0.261 and a standard deviation of 0.034. Sketch the probability distribution. So I'll just kind of do that over here. There's not a lot of space. So that goes right here. The mean is 0.261. I need to go thinner. All right. Now, if the standard deviation is 0.034, I'm going to take 0.261 and add 0.034. You get 0.295. And then I'm going to add, again, 0.034. You get 0.329. And the third one, I'm going to add 0.034 again and get 0.363. All right? Then I'm going to subtract 1, 2, 3 times. So back to 0.261 minus 0.034. I get 0.227. I'm going to subtract 0.034 again and get 0.193. And then I'm going to do it one more time, 0.034, and get 0.159. So these are batting averages along the distribution. All right? So find the probability that will have batting average less than 0.200. Well, where's 0.200? It's somewhere in that space. But we don't know what the z-score is. We know this one is -1 and -2 and -3. All right? So we know it's going to be between those two numbers. The z-score is going to be somewhere in there. So we just go back to that very simple calculation. Our actual score minus the mean divided by standard deviation. That's our z-score. Very simple. And obviously it's going to be a negative number. So 0.200 minus 0.261, enter, divided by 0.034. Oh, my bad. Silly me. Negative 1.79. It's between -1 and -2. I wasn't thinking. Sorry. Because right here is -1, here's -2. I was in the wrong section. So that makes sense. Negative 1.79. Now all you do is go to the chart for negative 1.79. Here's negative 1.7. Go all the way across. There it is. 0.367. So if we colored it in at 0.200 shaded left, that'd be about 36.7%. That's the probability that he'll hit under 0.200. All right? Keep going. Find the probability that it's greater than. Greater than. As soon as I see greater than or more than or right, I want to write this down and remind myself. 0.329. So that's the number we're going to plug into our very simple calculation. We're going to do the actual, seriously, 0.329 minus 0.261, same as before, divided by 0.034. And that's going to give me the z-score for that batting average. So 0.329 minus 0.261, enter, divided by 0.034. And that's exactly 2. All right, so what is that? -1. So I'm going to take that 0.329 and find out the z-score. 0.329 minus 0.261, and maybe some of you have already seen a shortcut, maybe not, 0.034. When you type that in your calculator, you get 2. So you're going to go to the chart and look at 2.0, and we've already marked it, 0.9772. 1 minus 0.9772. I think that's what it was. Yep. And when you do that, you get 0.0228. So that means about 2.28% chance of going above a 329 batting average. Okay? One more. So find the probability the randomly selected baseball player will hit between 0.193 and 0.295. Right. So we need to find out 0.193 and 0.295. We're going to do the exact same calculation. Minus 0.261 over 0.034. Minus 0.261, 0.034. So what's that going to give us? 0.193 minus 0.261 divided by 0.034. That gives us an area, oh, those are the ones we already did, silly me, of, it gives me a z-score of -2. And then 0.295 minus 0.261 divided by 0.034, that gives us a z-score of 1. All right? So we're going to look up those two areas. Okay? And subtract them. So 0.193 gave us -2. Wrong chart. So -2 is 0.228 or 0.228. Okay, and then +1, 0.8413. So all we do is subtract those. Minus 0.0228. And that gives us 0.8185. So 81.85% chance of it being between those two scores. And if you think about it, let's look at the chart, 193 and 295. 193 is here, 295 is there. That is about 88%, 81%, 82% of the graph. It makes sense. And that's it.